clearly transistors are on this layer here, devices, and we're working our way towards digital circuits. In the next video, actually, we'll finally make it to our desired destination, which is digital circuits. But we're actually going to bounce around quite a bit today. We're going to talk a little bit about this lower level of abstraction down here. Electrons again, even though we had already passed that in the first video, it is going to be worth talking about some of the physical layer stuff again, and we'll also maybe touch on some analog types of things throughout this video as well. So we're kind of in the bottom three layers for this particular video, and starting with the next video we're going to be in this layer of abstraction, and we're not really going to worry about these lower three layers very much anymore after we get through this particular video. Okay, so let's talk about transistors. There are actually two types of transistors that are worth talking about. And so here you can see the schematic symbols for both types. We've got N Mos transistors and we've got P Mos transistors. You see that they have the same pieces. So there's a gate, there's a drain, and a source on each of these transistors. And you'll remember from our last video, we talked about transistors as switches controlled by electricity. And so the gate in this particular case is the actual switch itself. The electricity is going to be applied to the gate that will turn the transistor either on or off. And so then when the transistor is on, current will be allowed to flow between the drain and the source. And it actually can flow in either direction. The direction that the current is flowing is not particularly important for our purposes, but you should know that it's going between the drain and the source. Now, the difference between N Mos and P Mos, you'll notice on the schematic diagram, the only difference between the two is this little circle here on the gate. And that's an important distinction. So what that means is, for an N Mos transistor, I have to apply a positive voltage to this gate. So I have to apply a 1 in the binary system to turn this gate on to allow current to flow through the system. If I don't apply voltage, if I apply a binary 0, in other words, then this transistor will be off and no current will be flowing from drain to source. The PMOS is the exact opposite. So in a PMOS transistor, if I apply voltage to the gate, if I apply a 1, a binary 1 to the gate, the transistor will be off and nothing will flow through. If I apply 0 voltage, or if I put it to ground, to use the electrical term, ground is equivalent to 0 voltage, then the transistor will actually be on and current will be allowed to flow through this particular transistor. So the switch will be active. It will be activated. So these are kind of complementary transistors, which is very important, as we'll see when we start to talk about the components of digital logic circuits in the next video. So how do these transistors actually work? I want to actually talk a little bit about the physics behind these transistors because I think it's particularly important. You've probably heard the word semiconductor thrown around when talking about computer chips, when talking about transistors. In this case, the semiconductor is going to be silicon. So over here on the very left, you can see we've got some silicon that is the primary component of all transistors. And by itself, silicon is not a very good conductor of electricity. To think of a real-world example of silicon, it's in a lot of rocks or sand, right? It's not exactly the same thing, but there's a lot of silicon in those substances. So it doesn't conduct electricity very well by itself. However, the reason it's so useful, the reason that we use silicon in our transistors, is because it does attach to other elements particularly well. So in this case, if you look at the middle diagram here, we've done what's called doping on this silicon. So we've added an atom of arsenic to this grid of silicon, which bonds very well with the surrounding silicon. The arsenic does. And so by adding this arsenic into the silicon system, we've managed to come up with an additional source of an additional positive source in the system, which is going to attract an additional electron into this silicon arsenic system. So we have an extra electron now floating around. An electron, of course, has a negative charge. So this system is what we call negatively doped. It has additional electrons available. than it would otherwise normally have if it were pure silicon. And then on the far right, you see we've got boron here in the middle, which is kind of the opposite, right? Boron has boron is going to boron is going to attract an additional electron, which means that the silicon will be missing an electron, right? So it wants an electron to be here, but there isn't one left because the boron has taken it. And so this is what's called a hole. There's an empty space where an electron should be, right? So this hole, this absence of an electron, can be thought of as a positive charge, which means that this is positively doped. Or in other words, we say that the arsenic doped silicon is going to be N-type, and if we use boron with the silicon, it's going to be a P-type semiconductor. So all transistors are composed of N-type and P-type semiconductors. And if you'll notice, if you'll recall back, we had two different types of transistors that were N Mos and P Mos. That's very directly related, as we're about to see. So we have these two types of semiconductor materials. When we combine the two together, we get what's called a diode. So here you see I've got some P-type semiconductor material with the boron and some N-type semiconductor with the arsenic placed side by side. This forms what's called a diode. You see the two parts here. Here's the schematic diagram for a schematic symbol for a diode down here at the bottom. The way a diode works, if the voltage of the P-type side is higher than the voltage on the N-type side, then current will flow through from left to right. It only goes in one direction, right? It can't go backwards from the N-type to the P-type. It can only go from the P-type to the N-type. And it will only flow if the P-type voltage is higher than the voltage in the N-type, right? If the P-type voltage is lower than the N-type voltage, then the diode is effectively off. Current cannot flow through at all. There is no current flowing through this particular diode. And so a transistor then is sort of comprised of these diodes. Let's take a look at what a transistor actually looks like. So on the left here you can see an N Mos transistor with the N and P semiconductor areas labeled. And then on the right side you can see this P Mos transistor with the P and N semiconductor areas labeled. And there you can also see the reason why they're called N Mos and P Mos. The reason it's called N Mos is because the source and drain are N-type semiconductors. These are called wells. The source and the drain are called wells that are embedded in a base layer of P-type semiconductor material. And then the PMOS is the opposite. The PMOS has two P-type wells, right, with an N-type semiconductor substrate layer forming the base. The other parts of the transistor that you can see, this polysilicon, or it actually used to be just metal that used to sit on top of the gate. And then underneath that, some silicon oxide, which you can think of as just glass. So remember, the gate is what controls the switch. The gate is what determines whether the transistor is actually on or off, as we're about to see here very shortly. And so there's kind of an insulation effect between the voltage that is or isn't applied to the gate and the actual substrate itself. So now that we know the pieces of the transistor, how do they actually work? Well, let's take a look at the operation of the N Mos transistor. Remember, the N Mos, the switch is on if there's a voltage applied at the gate, and it's off if ground is applied at the gate. So here on the left side, we see the gate is connected to ground. Ground is represented by this little empty triangle here. Right? So the gate is connected to ground. And recall from our discussion that there's actually diodes here. So these N wells in this P substrate form two diodes that you can see in this particular diagram, right? So in order for these diodes to be operational, the voltage of the P-type has to be higher than the voltage of the N-type. And in this particular case, the P-type voltage is 0. There's no voltage applied to it at all. It's applied directly to ground. And so the N-type is going to be 0 at best, right, or higher potentially, which means that nothing is going to be flowing through this transistor. It's essentially blocked off. If we want to turn this transistor on, if we want to flip the switch, we need to apply a voltage to the gate. So that's what we see here. VDD is a voltage that's being applied to this gate. And so here you see this positive voltage applied to the gate, which is going to attract electrons on the other side of the silicon dioxide, on the other side of this piece of glass. It's going to attract these electrons to these positive charges over here, to this positive voltage, and it forms a channel. So this channel is now effectively N-type semiconductor. We've effectively switched the type of this to N-type from P-type. And it creates a little channel that bridges the two N wells together and allows current to flow through between the source and the drain. In order for this to work, this voltage has to be above a certain level. That's called the threshold voltage. Typically this voltage is between 0.3 and 0.7 volts. So if I apply less than 0.7 volts, it's effectively grounded, it's effectively 0. If I apply more than 0.7 volts, that's effectively a binary 1. The transistor will be on, and it will be conducting current through this particular transistor. So just to kind of reiterate, right, we saw the physical specifications of how transistors work. We're not going to spend a whole lot more time talking about, you know, the electrons moving through the transistors, but this is the main takeaway from this particular video. Right, we have two different kinds of transistors, N Mos and P Mos, and they work sort of complementary to each other as switches. For N Mos, the switch is on if voltage is applied to the gate, and off if it's not. For P Mos, the switch is on if voltage is not applied to the gate, and off if voltage is applied to the gate. This is going to allow us to construct the basic building block of digital circuits, which are logic gates. That is the topic for our next video.